Hello, my dear friends. We continue to deal with some um, questions, theoretical questions, and assignments offered to applicants who wanted to continue their education at mo at most prestigious Russian universities because they wanted to become great chemists and physicists. I also hope that you find them interesting and useful for you. Well, so let's get started then without any delay. Here is the first assignment for you. It's theoretical, but it's not that easy to deal with. Right. So we got a VT diagram, which shows that some thermodynamical process of some ideal gas. Well, and the question is whether or not Q has been transmitted to the system. So by the system, I mean the ideal gas, which goes through this procedure, okay? Not procedure, this process, this thermodynamical process. Now, what should we start from? Well, let's get started from the fact that we are considering a thermodynamical process, which means that we can apply the mathematics of thermodynamics. In particular, that part, which is referred to the first law of thermodynamics. Let's write it down. So Q equals delta U plus A, where Q, as we understand, is the amount of heat transmitted to the system, or maybe taken from the system, taken away from the system. Delta U is the change of internal energy, okay? And A means expansion work done by the gas. Let's look at each of these parts of the equation one by one. Let's start from the change in internal energy. We see that during this process, the temperature remains constant. We can write it that during this process, the temperature remains constant, right? And that means that the temperature of the ideal gas at state 2 is equal to that at the initial point T1. And for that reason, delta T equals 0, yes? But let's remember the formula defining the change in internal energy. It is equal to nu, which stands for the number of the moles of ideal gas times C with index V, which means heat capacity at constant volume, times delta T. And if delta T equals 0, that means that delta U equals 0 too, right? And that means only one thing, that the heat transmitted to the system goes on the expansion work done by the gas. In other words, we should work with this moment. What should we know about A? When the system increases its volume, it does expansion work. And now let's take a look at the diagram. We see that V1 is the amount of the volume it has at the initial point, and V2 is the volume which it gets at the final state of the process 1 to 2. And we can clearly see that V2 is larger than V1. It means that the volume of the system goes up, and that means that the ideal gas we're talking about does some expansion work. It means that it is positive. If it is positive, it means only one thing. Q is equal to A, and that means that Q is also positive. What does it mean? It means that some heat has been transmitted to the system? This is the answer to this question. Thank you. I hope that you are ready to proceed to the next assignment. Hold a second, please. Here it is. To some extent, it is similar to what we have just considered. So again, we've got some ideal gas which goes through the thermodynamical process, which is shown depicted in the PT diagram, where this is the initial point of the process, while point 2 is the final state of the process. Okay, and the question is the same. Has any heat been transmitted to the system or not? So let's follow the same way which we applied when in the previous assignment. So U is equal to delta U plus A, right? Where delta U is the change in internal energy and A is the expansion work done by the gas. Let's find out what conclusion we can make about delta U. We understand that delta U is proportional to delta T, where delta T is the change in the temperature of the system, right? So we can see that this is temperature 1, and this is the value of temperature 2. We see that in this process, T2 is more than T1, which means that the temperature rises, and that means only one thing, that delta U is positive, right? Which means that it goes up. Now, what about the expansion work done by the gas in this procedure? To answer this question, we should, I guess we should see how the volume of the system changes, right? We remember that isocores of this process can be depicted by lines which go from the origin. Okay, here they are. I mean that this isocore corresponds to V1, while this isocore corresponds to V2, right? And we should remember, we talked about this in one of our previous classes, but they were in the Russian language. Okay, the main idea is that, you see, this is the angle between the isocore alpha 2, the isocore and the temperature x, right, axis, and this is the angle between this isocore and this axis, right? It's alpha 1. We see that alpha 1 is more than alpha 2, and that means only one thing, that V2 is more than V1. In other words, during this process, the volume of the ideal gas goes up. In other words, it expands. And if it expands, it does some expansion work. So A is positive 2. So what can we see? Delta U is positive, and A is positive 2. The two parts of this equation are positive. That's why its sum, their sum is positive 2. We can conclude that Q is also positive. And if Q is positive, it means only one thing. It must be as clear as a day for you that some heat, indeed has been transmitted to the system. This is the answer to this question. Thank you. So, I hope that you are ready to proceed to the next assignment. It's a problem which we must solve. Here it is. So 2 moles of ideal gas expands at constant pressure so that the concentration of its molecules at the final state is half as much as the initial concentration. Calculate the expansion work done by the gas. I'm sorry, not work by the gas. If its initial temperature equals T1. So let's get started then. We are asked to calculate expansion work. First of all, let's write down the common formula which enables us to do that. Is the integral of P dV, and the integration limits V1 and V2, right? But happily to us, the pressure is constant, and for that reason we can put it before the integration symbol. So we can write that it P times integral V1, V2, and V. The integral and differential symbols are two enemies. They destroy each other, and finally we've got PV, right? It means that it P times V2 minus V1, yes? So it's a common thing. I want you to understand where we got this formula, P times delta V, okay? I don't want you to take them automatically. I just want you to understand how we can derive these formulas. Don't take them for granted, okay? You must be able to derive them. Okay, and if we deal with ideal gas, for that reason, we can substitute this with this one, nu R delta T, right? Okay, or we can write nu times R times T2 minus T1, okay? Now, we see that P is constant, it remains constant, and that means the one thing that V1 over T1 is equal to V2 over T2, yeah? Okay, and we can express T2 from this proportion. It equals T1 times V2 over V1, yeah? Okay, but we have no information about the volumes of the ideal gas at states 2 and 1. We don't have direct information, but we've got a hint. The concentration. The thing is that concentration of molecules can be calculated as the number of its molecules in a particular volume. And from this, we can infer that the concentration of molecules is inversely proportional to the volume occupied by the gas. And that means that V2 over V1, we can substitute them with the concentrations of the molecules, right? And that'll be 2 and N1 because of this. So we can write that the temperature of the gas at the final state is equal to T1 times N1 over N2, where N, small n, stands for the concentration of the molecules of the gas. But we know that N1 is equal to Q times N, where Q is the coefficient, which is equal to 2. So we can write it that it's equal to T1 Q N2 times N2 over N2. So of the simplification, and finally we've got T1 times Q, right? And we can plug this into this formula. So we can write it, the expansion work done at the constant pressure is equal to the number of moles nu times the gas constant R times, instead of T2, we write T1 times Q minus T1. Now everything becomes very clear. So we've got the final formula for further numerical calculations. So A equals 2 moles, 8.314, yeah, joules per mole Kelvin, right? The initial temperature is 300 kelvins, right? And Q is equal to 1. We've got 100 joules, and this is what we actually need. And so if you get armed with a calculator, it will tell you that the numerical value to this problem is 4,988.4 joules. And this is the answer. Okay, thank you. So we are proceeding to the next assignment. It's taken from statistical thermodynamics. And I hope that you will find it interesting. Well, here it is. So the root mean square velocity of ideal gas contained in a closed vessel goes up by 20%. How many times does its pressure change then? So from the course of statistical thermodynamics, we know that there are several types of velocities of molecules we usually deal with. One of them is this one, root mean square velocity, right? It can be calculated as the square root out of 3 times k times t over m, where k is Boltzmann's constant, right? T is the temperature, and m is the mass of one molecule of the gas. But the thing is that we have no idea what gas is being considered in this problem, and we should find a way out somehow. So the solution is the following. So if we multiply the numerator and denominator of this fraction to the same number, it will change. It won't change at all. And I offer that we multiply the numerator and denominator to Avogadro constant. Okay. In this case, the multiplication of constant Boltzmann to Avogadro Boltzmann gives us the gas constant R. Okay. So we've got 3, it remains 3 R times T. And the multiplication of one molecule to the Avogadro constant gives us this one. It's the molecular, it's molar mass of the gas, mu. Okay, it's a bit better. Now it's a bit better. But it's not very convenient for us to deal with square root. For that reason, I offer that we raise the both parts of this equation to the second power, and we will get the following. V squared is equal to 3 times RT over nu, right? Okay. And if we deal with ideal gas, we can use the ideal gas state equation. P times V equals M times R times T over mu. Okay. If we compare this with this, we can see something similar. For example, this part is contained in this formula too. Yeah, I guess it's a very good thing for us. So let's express r times t over mu from this formula. So r times t over mu equals v squared over 3, okay? And substitute it with this here, and we will get that v equals m, and in this case, m is not the mass of one molecule, okay? It's the mass of the gas. And to differentiate this to m, so I will write m with index O, which means that it is the mass of only one molecule. So and finally, we've got m times v squared over 3. Okay, and we need to find the relations between two pressures, and that gives me the idea what I should do next. I should express P from this equation. So P equals m times v squared over 3 volumes. Okay. So we can now express P2 and P1 through the velocities. So I can write that P1 is equal m over 3v, v1 squared, okay? And I can write that P2 is equal m over 3v times v2 squared, right? But v2 is 1 plus alpha v1 times v1. Why? Because it goes up by 20%, and we don't usually work with persons, so we work with parts. For that reason, 20% means 0.2. And if it goes up, I should multiply v1 to 1 plus alpha. In other words, I can write that P, the second pressure, is equal to m over 3v 1 plus alpha times v1 squared. Okay. So now we can find the relation between the pressures. So it's m over 3 1 plus alpha squared v1 squared. This is what P2 equals to. And I divide into P1, which means that I should write it the following way: 3v over m v1 squared. So we simplify because it is obvious. And finally, we've got 1 plus alpha squared, right? Now I plug the numerical value of alpha. It's 0.2 squared is 1.2 squared. It means 1.44. This is the answer. So we say that the pressure of the ideal gas goes up by goes up 1.44 times. And this is the answer to this question. And we are proceeding to the next question. It's rather theoretical, and we have already looked at similar assignments. So let's consider this problem. The problem is the following. So let me translate it from Russian into English on the second page. Yeah, okay. We've got idle gas, and we should believe that we know its as a call heat capacity, which is equal to C with index V. Okay, and this idle gas goes through a thermodynamical process such that P, the pressure of the gas, is proportional to its volume. And they ask us to derive the formula of its molar heat capacity C. So the procedure is standard. We used it in the previous, one of the latest video clips. So let's follow it. Let's follow it. Okay, so we remember that Q is equal to delta U plus A, right? According to the first law of thermodynamics, where Q is the heat of the system, delta U is the change in internal energy of the gas, and A is the expansion work done by the gas, okay? Q, in turn, is equal to the number of moles of the gas, nu times C. It's molar heat capacity times delta T, the change in temperature. And this is our target, okay? Delta U is equal to mu times CV times delta T, okay? And the situation with A isn't clear. And this is our next step to identify, to derive a formula, which will show us the way how we can calculate the amount of work, expansion work done by the gas as a result of this process, which is characterized by this gas behavior equation. What can we do? First of all, let's remember that A is traditionally calculated with the help of the integral PdV, and the integration limits are V1 and V2, the initial and final volumes of the system. Okay. So far, so good, I would say, but I wouldn't, because it's not clear yet what we do next. We've got dV, right? We've got dV. We also know that we deal with ideal gas, which means that we can and should use its state equation, which is P times V equals mu RT. Yeah. Okay, let's express V from this equation. It's mu RT over P. But remember that P is equal to alpha times V. V equals mu RT alpha V, right? Which means that V squared equals mu times R times T over alpha, right? We need to find delta V, differential of the volume. So let's do that. We take the differential from the left and the right side of this equation. And we remember that differential of, for example, x raised to m is equal to m times x raised to m minus 1 dx, right? So if we follow this formula, d of v squared is equal to 2 times v dv. Alpha r and nu are constant. We can therefore put them before the differential symbol. It equals to mu r over alpha dt. Okay, now we see that dv goes to dt. For that reason, the integration limits based on the change in volume transforms into this change in temperature. So we can write that R is equal to B. Instead of dV, we write what it equals to. I haven't written it down yet. So dV is equal to mu R dt times 2 alpha V. Okay. So instead of dv, I write this one nu r dt over 2 alpha v. And now we integrate from t1 to t2 because we've got t after the differential symbol. But p is equal alpha v, right? So instead of p, I write alpha v mu r dt over 2 alpha v. Alpha, v, and v go. And we've got finally mu r over 2. They are constant for that reason. I can write them before the integration symbol. Okay, dt. The integral and differential kill each other, and we've got mu r over 2 minus 2 1, or it's equal to mu r over 2 delta t. So we can put this instead of a into this formula. Instead of q, we write mu times c times delta t equals, instead of delta u, we write mu c with index v delta t. Instead of a, we write what we have just derived, mu r over 2 times delta t. So mu goes, delta t goes as well, and finally we've got c is equal to c with index v plus r over 2. This is the formula which allows us to calculate the heat capacity of ideal gas which complies with this behavior characterized by this formula. Hello, my dear students. I guess it's high time that we started to look at more challenging questions, more challenging in theoretical terms, because the problem is that a great number of chemists tend to get used to dealing with standard ways of dealing with problems, quantitative problems, and for that reason, if a challenging assignment or problem asks them to do something they have never done before, so they get lost. And in order to overcome this problem, I have prepared a set of problems where they will ask, or you will have to deal with something which seems to be unusual. By unusual, I mean that the equations of the state are not widespread, and they can be given only in imaginary world, I would say, because you will never come across a gas which complies with this or that equations which describe its state. Okay, so let's get down to the nitty-gritty, as the Americans say, which means let's get down to the business without any delay. Well, the first assignment is the following. It's number 1. Okay. So in this assignment, they ask us to derive the formula of work A, heat Q, and the change in internal energy, delta U, for a process in which ideal gas go through some changes which can be characterized by the following equation. P times T equals V. I hope you understand that P stands for pressure, T is the temperature of ideal gas, which we are considering, and B is some constant. So we can write that B is constant, okay? And according to this assignment, we are supposed to derive the formula which would enable us to calculate the work done by the gas, the heat transmitted to the gas, and the change of its internal energy delta U. Okay, so let's start from applying the equation of the first thermodynamical law, which is let me change the color. Q is equal to delta U plus A, right? This is the mathematical interpretation of the first law of thermodynamics. Okay. Q in turn, Q is nu, which is the number of moles, times C, which is the heat capacity of this gas, and delta T, which is the change in the temperature of the gas. Okay. In turn, delta U can be calculated as nu times isochoric heat capacity CV, C sub V, okay, and delta T. Okay. So the problem is about A, or work. I know that in modern physical chemistry textbooks, work is denoted through the letter W from the English word work. However, it's also widespread. It's a widespread tradition to denote work as A, because it's the first letter of the German word Arbeit, which means work. Okay, it doesn't matter how you denote work, through W or through A, it doesn't matter. So A can be calculated as the integral from V sub 1 to V sub 2 of B dV, right? Okay. We should remember the fact that we are considering the behavior of ideal gas. And for ideal gas, its state equation is P times V is equal to nu times R times T, right? Okay. And also, we remember that particularly in this process, the main equation which describes the changes is Pt equals B. Let's express B from this equation. It, for example, P is equal to B over T, right? B divided into T. And we can plug it, right? For example, here, into this formula, we will get B over T times V is equal to mu RT. In this case, if we express V from this equation, we will get the following. V is equal to nu times R times T squared over B, correct? And now we can calculate the differential of the volume, dV. So dV is equal to d of this fraction, nu RT squared B over B. But we can see that nu, R, and B are three constants, which we can put before D, and we will get that it's equal to mu R B times D of T squared. And we can calculate the differential of T squared very easily. 2 will go here, okay? And we will get finally 2 nu R T times dt over B. This is what dV is equal to 2. And for that reason, we can substitute, we can plug in this expression instead of dV and this instead of B. And finally, we get the following integral. So integral from V sub 1 to V sub 2, B over T times 2 nu RT dt over B. And we can simplify this fraction by reducing it. B over B, T over T. And finally, we get the following. 2 times nu times R, the gas constant, right? Integral, and I'm sorry, not V, but T1, T sub 1 to T sub 2, because now after under differential, we got temperature, but not V. So T1, T sub 1 to T sub 2 dt. We remember that the integral and differential are two opponents, and they say goodbye to each other. Finally, we got 2 times mu times r d sub 2 minus d sub 1. Okay, we have got what we need, but to be on the safe side, let's express this formula not through temperatures, the initial and the final temperature of the ideal gas, but through its temperatures. I'm sorry, through its pressures, initial pressure and final pressure. So how can we do that? It's very easy. B is constant, right? Which means that P sub 1 times T sub 1 is equal to P sub 2 times T sub 2. Okay? And in this case, we can write that T2 is equal to P sub 1 times T sub 1 over P sub 2. And let's plug this here instead of T2, T sub 2. And we will get that A is equal the following. Okay, and also, in order to simplify it finally, we can put T1 before the round brackets, and we will get 2 nu RT1 times P1 minus P2 over P sub 2. This is the final formula, which enables us to calculate the work done by the ideal gas, which goes through some thermodynamical process, which is characterized with this equation. As for the change in internal energy, it's very easy to do. We've got this formula. Yes, here it is. So T sub 2 minus T sub 1. And if we do the same manipulations as we have just done with the work formula, we will get that it's equal to sorry, it's P1, P sub 1, right? P sub 1 minus P sub 2 over P sub 1. This is the formula for the change in internal energy. As for Q, we can apply the first law of thermodynamics formula, Q, and we'll get that Q is equal delta U plus A. It means that we should sum these expressions. Okay, and for work we got this one. Okay, and in order to simplify it 100%, so let's factor it, and we put nu times T sub 1 times P sub 1 minus P sub 2 over P sub 1 times C sub V plus 2 times the gas constant R. That's it. This is the formula for Q. As you can see, we have had to deal with integration and differentiation in order to get these formulas. Thank you. I hope that it is clear for you how we've got these formulas. And now we are proceeding to the next assignment. Um, the next assignment is the following. Again, we are dealing with ideal gas, which go through a thermodynamical process, which can be characterized with the following equation: P squared equals alpha times T, where alpha is some constant. Okay. And again, we are asked to derive formulas for the work A, heat Q, and the change in internal energy delta U for such ideal gas which goes through the process which is characterized by this formula. Okay, so let's start from the very beginning. Okay, um, let's express pressure from this equation. So P is equal the square root out of alpha times T, right? It's clear. Also, we remember that we're dealing with the ideal gas. For that reason, its state equation is applicable. So let's write it down. A pressure uh, times volume equals mu RT. Okay. So, and let's insert this into this equation instead of P, and we will get the square root out of alpha times T times V is equal mu RT. Okay. And from this equation, V is equal the number of moles R times the gas constant R times T over the square root out of alpha times T. We can reduce this fraction this way. So traditionally, let's start from deriving the formula for work A, which can be calculated with the help of this integral, integral from v sub 1 to v sub 2 of p dv. Okay, and now we can plug the square root out of alpha times t instead of p in this integral. And now we need to find out what dv is equal to. And I guess I have written this a bit then I should have done it. Okay, hold on a sec, please. So let's first of all identify differential of the volume dV. So dV is the differential of this fraction mu r the square root of alpha times t raised to 0.5. Yes. Okay. These are constants. For that reason, we can put them before the differential, and we will get mu times r over the square root out of alpha. And if we differentiate the square root out of temperature, we will get mu times r over twice the square root out of alpha. Yes, and t raised to minus 0.5. Yes. Yeah. Or let me rewrite it in more traditional form. Okay. And now we can write the integral to identify the work done is from the integration limits from v sub 1 to v sub 2 of the dv. Okay. Instead of b, I write this formula, okay? And instead of dV, I write this one. Yeah, here, of course, dt. As you see, now the integration limits change from volumes to temperatures, because after differential symbol, we've got temperature but not volume anymore. Okay, now we can see that we can reduce this fraction. And finally, we got this situation. It's very good because it's easy to do with. So we've got this formula. It's nu times r over 2 and times t sub 2 minus t sub 1. Or it's I guess it's more appropriate to express the formula not through temperatures but through pressures. Let's do that. We can write alpha is constant. For that reason, we can write it p sub 1 squared over t1 is equal to p sub 2 squared over t2. And let's express the second temperature from this proportion. It's equal to t sub 1 times p sub 2 squared over p sub 1 squared. Okay, and let's plug it in into this formula. And finally, we'll get that A is equal to nu times R over 2 times T1. Yeah, I guess it's very clear what I'm writing. So we can factor it by putting T1 before the round brackets, and we'll get nu times R over 2 times T sub 1 times, and within the brackets we write p sub 2 squared minus p sub 1 squared over p sub 1 squared. And this is the final formula, which allows us to calculate the work done by the ideal gas, which is considered in this problem. As for the change in internal energy, it's very easy. Delta U is equal to mu times C sub V times t sub 2 minus t sub 1. Yes, and we do the same procedure as we have done with the work formula. And finally, we get that it's equal to mu times C sub V times t sub 1 times p sub 1 sub 2 squared minus p sub 1 squared over p sub 1 squared, right? And as for Q, we remember that Q is equal to delta U plus A, and that means that Q, and let's substitute instead of delta U this formula, instead of A this formula, and if we do that, finally we can get the following formula. Yes, okay, over that's it. So these are the three formulas we are supposed to derive in this problem. This is the formula which enables us to calculate the amount of work done during this process, which is characterized with this equation. This is the formula for the change in internal energy, delta U, this one. And this is the formula which allows us to calculate, enables us to calculate the amount of heat transmitted during this process. Thank you. As you see, the approach, the solution approach applicable to this problem is identical to the previous one. Well, it enables us to find the right answers to the questions offered in this problem. Now we are ready to proceed to the next problem. The assignments or the questions in this problem are similar to the previous two ones. Again, they ask us to calculate, to derive the formulas calculating the work A, the heat or the heat Q, and the change in internal energy delta U. Okay, for the ideal gas, which goes through a thermodynamical process, which is characterized by the following equation: T times, T equals beta, which is constant, times the square root out of pressure P. That's it. So again, let's start from A. We remember that A can be calculated with the help of the integration. And the integration limits are from v sub 1 to v sub 2 of P to V, right? So we can derive P from this equation if we raise the left and the right side of this equation to the second power, and we will get that T squared is equal to beta times P, right? And from this, we can express P very easily. It's T squared over beta, okay? So we've got it. So far, so good, but we don't know anything about dV. To know what dV is equal to, we first of all should work out the formula of the volume of the ideal gas. And it's high time to remember that we are dealing with ideal gas, and for that reason, its state equation is applicable. So P times V is equal to mu times R times T, right? So let's substitute P with this expression, and we will get that T squared over beta times V is equal mu times R times T. As we can see, we can reduce this equation into T, and we will get finally that T over beta times V is equal mu times R, right? Let's express V from this equation is equal mu times R times beta over T, right? And now we can derive the differential of the volume. So dV is equal d of mu R T raised to minus 1. Yes. Okay. So nu and R are two constants, which enables us to put both of them before the differentiation. And we will get that dV is equal to mu times R. And if we differentiate the temperature raised to minus 1, we will get minus 1 times T raised to minus 2 times dt. More traditionally, it looks like this. Okay. Now we've got P, we've got dV, and now we are ready to integrate. But we should take into consideration the fact that the integration limits have changed from volumes to temperatures. Now A is the integral from T sub 1 to T sub 2, and P is equal to T squared over beta, and dV is minus, let me write down minus before the integration immediately, okay? Nu times R over T squared dt. Again, very good thing is that we can reduce this fraction, and we will finally get that it's equal to minus mu times R over beta. Yes, over beta. Okay, integral T1 from T sub 1 to T sub 2 of dt. Just very easy to deal with. Is equal this one. Wow, that's great. That's great. So this is the formula, but To be on the safe side, let's substitute the temperatures which are included into the formula through pressures and the constant beta. So as B is the constant, we can write that T sub 1 over the square root out of P sub 1 is equal to T sub 2 over the square root out of P sub 2. And from this proportion, we can express T sub 2, which is equal to T sub 1 times the square root of P sub 2 over the square root of P sub 1. Okay. And now we can plug it into this formula instead of T sub 2. And we can write that A is equal to minus mu times R over beta. T1. Okay, you understand what I'm writing down. I've got T sub 1 here and T sub 2 here, and that allows me to write the following. Yeah, okay. So this is the formula which we have to write for the work. Yes, but to say goodbye to this minus, so I can put it inside these round brackets, and that will make me put the two parts to put them into different places. So that finally I'll get this one. Yeah, here it is. So this is the final formula, which enables us to calculate the work done by the gas in this thermodynamical process. As for delta U, again, it's very easy to do. We do the same manipulations with T sub 2 and T sub 1. We plug in this expression instead of T sub 2 into this formula, and finally we'll get the following is equal to mu times C sub V times T sub 1 . Okay. And as for the amount of heat, let's remember that we deal with thermodynamics, and for that reason, the first law of thermodynamics is of course applicable because it's universal. And we will get finally this expression. So we can see that in this part we got the same things, and we can write that Q is equal to yes, and C sub V minus R. This is the formula to calculate the heat of the process. Thank you.